In this video, we shall be discussing a few numerical examples to understand the topic that we discussed in classical mechanics, that is the two-body central force. To begin with, we have the first problem, which says a particle of mass m moves under the action of central force whose potential is expressed as Vr, which is equal to kmr cube. It's actually ur instead of Vr. We have been using the general form of the potential energy as ur instead of Vr. So we'll be continuing with that. That is ur, just to avoid the confusion. And that is kmr cube, k greater than 0. So we have to obtain the kinetic energy and the angular momentum, for which we are going to get a circular orbit of radius r, capital R that is, and also we are to calculate the period of motion. Now, as from the given case, we can find the solution in the following manner, where we first have the potential energy, which is kmr cube, and so with the conservative force that we express, we have a del u over del r, and that is equal to minus of 3 kmr square. It's a negative gradient of potential, the conservative force. And so for circular motion, this force has to be of the form of centripetal force. So we have force to be equal to mv squared over r, negative taken because it is directed towards the center, and this is obviously minus of 3 kmr squared. Now comparing, what we get is that the r can go to the right hand side of the equation. We have mv square to be equal to 3 kmr cube. Now taking or multiplying half on both the sides, we have the, guess what, the kinetic energy that we were supposed to obtain. So the kinetic energy that we were to obtain is 3 over 2 kmr cube. That is the first part of the first answer. As far as the angular momentum is concerned, we have mvr to be its expression, and mvr simply is equal to mr times of v. Now because we have the expression for kinetic energy, from that we can obtain the value of v. Now v here is going to be equal to, the m's cancel out on both the sides, 2's cancel out, in the denominator we have 3 r cube, 3kr cube. So that is the value of v under root. So root over of 3k r cube, that is the value of v in that case. So mr times of v, which is 3k r cube under root, and that is the expression. We can get the r together, and to the power 1 to the power 3 over 2, so that gives 5 over 2. We can do that. So m r 5 over 2, 3k lies within the or under the root. That's the expression for the angular momentum. So these are the two things, not this one. We were to obtain this one. So these are the two things that we were supposed to obtain in the first part of the answer. So that's done over here. Now, as far as the second part is concerned, we wish to obtain the time period of the circular motion. Now, the time period in this case, v, as we know, is equal to r times of the angular speed, which is omega. So r times of omega is nothing but 2 pi over t, which is the time period. So the time period in this case is equal to v over 2 pi r. And as we have obtained the expression for v, so we have obtained the expression for t as well. So t will be obviously equal to, now v is equal to root over of no, so this is sorry, that's the other way around. It's not actually v over 2 pi r, it's 2 pi r over v, and 2 pi r over v is going to give me 3k r cube under root. But as we can see, there's an r over there and an r in the denominator term. What we get from that is simply the r can go over to the denominator. Conversely, from the denominator we can take an r square out, and that will cancel out the r in the numerator, so we will have t to be equal to 2 pi. The r has cancelled out with the r square under root, and one of the r remains in the denominator under root. So that is the expression for time period in that circular path that it takes. So that's the first example that we have discussed. Right now we move over to the second one, which says it involves eccentricity of the Earth's orbit, which has been provided to be 0.0167. 0.167 is obviously 1 over 6, so 0.0167 is going to be 1 over 60. We'll come back to that. Now we are supposed to calculate the ratio of the maximum and minimum speeds of the Earth in the orbit. Now, as the Earth orbits about the Sun, obviously it will be orbiting about the Sun. So in that case, what we will be getting is that the speed increases to a maximum value as it comes close to the Sun, that is at the perihelion, where the gravitational pull due to the Sun is maximum, and hence it contributes to the velocity. And it has a minimum speed, or it achieves a minimum speed when it is at the aphelion, where it is to the greatest distance from the Sun. Now both these conditions can be dealt with the common or the general expression for the equation of the conic. We need not be concerned about the expression completely as a whole, but just a case of it that says that we have the expression as L over R to be equal to, now this is the solution that we are moving forward with. L over R is going to be equal to 1 plus E cosine of theta minus theta dash. That was the general expression, but theta in this case, as we are considering the Sun supposedly over here, and the two positions that we are considering is one over here at the perihelion and the other over here at the aphelion, and both the distances are at 180 degrees difference. So if one of the positions is taken to be 0 degrees, then the other one will be taking an angle of 180 degrees. So this is the closest distance that we have, that is, let's say R1 this is, and this one's R2, as we had expressed in our deduction of the Kepler's third law that we were that we had discussed in the theory section. So L over R1 over here is 1 plus E, and L over R2 is going to be 1 minus E, considering cosine of 180 degrees over there. Now if we take the ratios of both of them, what we are going to end with is the ratio of the first to the second is going to yield R2 goes up, R1 goes down, and we have 1 plus E over 1 minus E. Now the constancy of the angular momentum, it tells us that mv at R1 and mv R1 will have to be equal to mv at R2, but the velocities corresponding to that is supposedly this is R1, we are taking it as max, and this one is the minimum. So we have taken it's clumsy, looking clumsy. I'm taking it as v1 v2 for now, or I can erase the whole of thing and then take it as v max and v min. and I choose the latter. So what we have over here is a V max, the m's get cancelled out, so V max over V min is going to give me R2 over R1, which is exactly the thing that we have onto the left hand side of this equation. So that will finally be equal to 1 plus E over 1 minus E, and we know the eccentricity as I expressed it, it's 1 over 60, so it will be 61 at the top divided by 60, and then it will be 59 at the bottom divided by 60. The 60's get cancelled, and this is a little over 1, goes to approximately 1.03. So this is the ratio of the maximum and the minimum speed that is acquired by the Earth in its orbit, that has been provided with an eccentricity of 1 over 60, or that value that we see. Now we can establish a relation between eccentricity and the ratio of the maximum and the minimum speeds. We already have one over here, but we would also like to take the other way around. We just cross multiply them. We have V max plus V max E is equal V max minus V max times of E, that is the eccentricity, if that cross multiplies, and V min plus V minimum times of the eccentricity. So the eccentricities can come together, and we have the expression as a V max minus the V minimum over V max plus the V minimum. It's quite easy to remember because the numerator term is going to be less than the denominator, which will provide us the eccentricity to be less than 1 in case of orbits such as that of the Earth. In other cases, as the case of eccentricity may be, we will be having the relation as that. But this is more or less a general expression that we can use to solve various cases. Then moving over to the next question, what we have is, a particle of mass m is observed to move in a spiral orbit. Spiral does not necessarily mean that it is a circular orbit. So spiral orbit given by the relation r is equal to c theta, where c is obviously a constant, and we have been tasked to obtain the case that whether the motion is in a central force field or not, and then next, if it is in a central force field, then we are supposed to obtain the force law that governs it. Now, as far as the solution is concerned, we proceed with what we have at hand. First things first, the differential equation for the orbit, the general expression can be given as d2u over d theta square. Remember, u is 1 over r, so we'll be using that. So this is the more general way of representing it, d2u over d theta squared plus u is equal to minus m, and this is the force that has been provided, which depends on r, or conversely 1 over u, divided by the j square u square, j being the angular momentum and u being 1 over r. So u is 1 over r, and r is equal to c times of theta that has been provided. So what we get to know is u will be equal to 1 over c theta. Now du over d theta, that is that we are going to use in that equation above, actually the double derivative of that. So we have 1 over c theta squared for the first case, and then d2u over d theta squared is going to give us 2 over c theta squared, actually 3 c theta cube, and that is going to result in 2 times of c square u cube, because as you know that theta is equal to c times of u, the reciprocal of c times of u, so that's going to be c cube u cube, and the c gets cancelled out in the denominator to one of the c's at the top. So this is the expression for d2u over d theta squared. We are going to use that in that above equation. So we have this equation over here, and using this expression that we have for the double derivative term, so 2 times of c squared u cube plus u is going to give me minus m over j squared u squared f of 1 over u. So that finally gives me the expression for f of 1 over u to be equal to, now that term that is there, that cross multiplies to the other side, so we have minus of j squared u squared over m, and this thing completely in brackets c square u cube plus u. Now that u square can go in, and what we'll have is u cube in the first term. Well, this is more or less the expression that we are seeking for, because yes, it is in central force because it is in the negative form of when we write that in form of r. So j square over m remains outside, u square is 1 over r squared, and u cube is 1 over r cube. So this is 2c squared over r to the power 5, and the second term that we have is simply u cube, which is 1 over r cube. So this is because the form of it is the negative of it is the central force, conservative in nature, is provided with a negative force that we have, and that is why this is the central force field, and the force law that governs the central force field over here is the expression that we have at hand at the end, which is this one. So both our objectives have been achieved. Now moving over to the next question, next example. This is more or less to show that the particle that is describing a circular orbit under the influence of an attractive central force is which is directed towards the center, or towards the point on the circle. We need to show that the force varies as the inverse fifth power of distance, that is 1 over r to the power 5. Now we'll use a diagram to help us get to this. So this is the circular path that it's taking, the particle that is, and in that circular path, supposedly it has a radius a, and it is the particle is over here. During its course, it has the radius is a, and the angle is supposedly theta at this point. So this distance that we see is going to be constant with respect to the center. So it is ideal that we take it from the diametrically opposite point. We take it from over here, this distance, we'll take it as r. Instead of taking that, this is alpha. At any given instant of time, we have a theta corresponding to another angle alpha with respect to, let's say this is the origin, so we have p to be having the coordinates r and alpha over here. Now with these coordinates available to us, the polar coordinates, that is, we have r to be equal to 2a, because this is a as well. So 2a cos alpha, cosine of alpha. The differential equation that we will be using is obviously d2u over d alpha squared in this case, because we are taking the angle to be alpha, plus u is equal to minus m times over j square u squared f of 1 over u, which is the one that we used above. Now in that, because u is equal to 1 over r, and that is going to be 1 over 2 alpha 2a cos alpha, so that is going to give us u. So du over d alpha is going to be equal to 1 over 2a sec alpha tan alpha. Then again d2u over d alpha squared is going to give me 1 over 2a, that remains outside, and in the bracketed term derivative of the first can be left as a constant, and the second derivative will give me sec square theta for tan, sec square alpha for tan alpha, and that multiplied to sec alpha is going to give me sec cube alpha. And then we keep the first term as such, that is sec alpha, and the derivative, now the second term, that is tan alpha, that is to remain, and for sec alpha we are getting sec alpha times of tan alpha, and there was a tan alpha over there, so tan squared alpha. You can do the derivatives yourself and check the value that comes out to be exactly the same. Now we use this value in that. Now over there we will also need u is simply sec alpha over 2a, to put things properly. So again we bring this equation back and we put these values. We have 1 over 2a. Now we can directly put f1 over u, and onto the other side we have j squared u squared over m, as in the negative, and the bracketed term involves well, we can take the 2a out as well, because that is common to everyone, including u. So we take that out, and within the brackets we have the first term for d2u over d alpha squared as sec cube alpha plus secant alpha tan square alpha, plus the last term being sec alpha for u. And then the tan square term, that can go to sec square alpha minus 1, and when we multiply that to the sec alpha, so that is sec cube alpha minus sec alpha, so this term and the negative term are going to cancel out, and with them getting cancelled out we have 2 sec cube alpha over there, so this is minus j squared u squared. 2 cancels out with the 2 in the denominator, so we have am sec cube alpha. So that's the expression for now what is the value of sec alpha? Well, sec alpha is equal to 2a times of u, if you see that, and u is 1 over r, so it is actually sec alpha is, from this part we know that to be equal to 2ua, or 2a times of u is 1 over r, so we take it as 2a over r, and we put it over here, so we have j squared u squared now is 1 over r squared, am the 1 over r squared, and this is 2a cube r to the power 5. So all that we have got over here is what we wanted, that it is inversely proportional to the fifth power of the radius in that case, and that is, or the distance in this case, so that has been obtained. So I'll be ending this video over here. We'll be dealing with few more of them on this topic in the upcoming videos. Till then, thank you for watching.